The curvature of spacetime plays tricks on our eyes. Much of the deep universe is shifted and magnified by the warping effect of gravitational lensing. Our brains evolved in a Euclidean world, or pretty close to it. We have hardware to build internal models of our environment in which space is a simple 3D grid, static with time. In the world of our mind's eye, light travels in straight lines. This lets us map the real world into the imaginary. We just catch photons with our eyes and trace their paths backwards. This works beautifully as long as those light paths are truly straight. But add a pool of water, or a glass lens, or a funhouse mirror, and our internal model fails. We perceive illusory and distorted images as our mind's eye tries to enforce oversimplistic physics on a complex reality. Well, it turns out that the whole universe is a giant funhouse mirror, a rippling pond, and many things are not where or what they seem. In the real universe, both space and time can be curved, and the path traveled by light follows the curve. Here's our playlist on curved spacetime if you want to go deep into this idea. Einstein's general theory of relativity describes the real universe as a flexible, dynamic, dimensional grid that only resembles our mind's eye Euclidean lattice in the absence of mass and energy. The curvature produced by mass gives gravity. Light follows this curvature, and so gravity bends the path of light. The prediction of general relativity that gravity deflects the path of light rays was one of the first to be directly verified. In 1919, British astrophysicist Sir Arthur Eddington loaded a ship full of astronomers and set sail for the island of Principe off the west coast of Africa, and sent a second ship to Brazil. The mission? To catch an eclipse of the sun and to measure the tiny change in the position of nearby stars due to the deflection of their light by the sun's gravitational field. And here's the photo he took during the eclipse. The stars had shifted. Their light paths were slightly deflected, making them appear a bit further from the sun. The deflection angle was exactly what Einstein's theory predicted. This particular confirmation of general relativity was the one that shot Einstein to his great fame. The New York Times article is wonderful. I find it especially touching that it assures us that we need not worry about the dangers of gravitational lensing, which is, of course, what we've come to call this phenomenon. The gravitational field of any massive object converges passing light rays, like a badly designed lens. For stars, this effect is typically small, and Einstein originally felt that it would be a cute but subtle and not particularly relevant phenomenon. That's not the case. When we look out there at the universe, we see gravitational lensing everywhere. It's become a very powerful tool for studying the universe. At its most spectacular, we see extreme warping of the shapes of distant galaxies as their light travels through the deep gravitational wells of intervening galaxies and galaxy clusters. They are greatly magnified in brightness and stretched into arcs and rings. These are beautiful, but they're also useful. The illusion results from our mind's eye projecting straight lines onto a curved spacetime. When brains don't suffice, we instead build model universes in our computers. Their spacetimes can curve any way we choose. Within these simplified virtual universes, we can hunt through vast possibility space. Somewhere in that parameter space is a configuration of lens and light source that will collapse those distorted images into the true galaxies that created them. Find that configuration, and we've mapped the gravitational field, the distribution of mass of the lens. We've weighed many galaxies and galaxy clusters this way, and we've confirmed that the vast majority of mass in this universe is in the form of dark matter. When the distortion of the light source is this obvious, we call it strong lensing. But the phenomenon doesn't just distort and magnify. Sometimes we see the same object through multiple paths through space. This is the Einstein Cross, an extremely luminous, distant quasar, powered by a supermassive black hole feeding on its surroundings. In fact, each of these spots is that one quasar, viewed via 4 different paths through the universe. You can see the nearby spiral galaxy whose gravitational field bends space-time to create these paths. To see multiple quasar images, you need a near-perfect alignment between the lensing galaxy and the quasar. While we know of a couple of 100,000 quasars, we only know of about 100 that are lensed this way. The flickering of the lensed quasar images carries with it many secrets. The quasar is a vortex of superheated matter falling into a black hole. This is a violent, fluctuating process. By measuring the time delay between fluctuations for those different paths, we can actually measure the path lengths. Distances are one of the hardest things to measure in astronomy, but are essential for cosmology. Lensing distance measurements have allowed us to measure the Hubble constant, which tells us the rate of expansion of the universe, independently confirming the results from other methods. Also coded in this flickering is information about the heart of the quasar itself. Light passing through the starry lens galaxy brightens and dims due to the gravitational fields of individual stars in that lens, in a process called microlensing. As those stars sweep in front of the quasar's inner vortex, its different parts change in magnification to different degrees and at different times. We can read this flickering to map regions near the black hole, many orders of magnitude smaller than any telescope could resolve. Although this sort of obvious strong lensing is rare, the effects of gravitational lensing are everywhere. Weak gravitational lensing slightly warps the shapes of essentially all galaxies in the universe. When we look at hundreds or thousands of galaxies, we can spot correlations in the way their elongations are aligned. We see that they encircle the vast strands and nexuses of dark matter that form the cosmic web, allowing us to understand its structure. Even within the Milky Way, we see the effect of lensing. Compact stellar bodies, black holes, neutron stars, and brown dwarfs occasionally pass in front of other stars and lens them into brief flashes of increased brightness. This is how we've been able to count these otherwise near invisible stellar bodies. Despite Einstein's pessimism, gravitational lensing has become an important staple in the astronomer's toolkit. It's allowed us to decode the universe in ways that would have been impossible in boring Euclidean space. Of course, the most extreme gravitational bending of light results in the most awesome of all astrophysical objects, the black hole itself. The light speed flow of spacetime at the event horizon results in all light paths pointing inwards. This gives us the black in black hole. Light falling below the event horizon is lost forever, so we don't describe it as being lensed. But just outside the event horizon, we find the most extreme gravitational lensing in the universe. The photon sphere hovers at about half again the height of the event horizon. This is a region where light paths are so strongly curved that photons can actually orbit the black hole, forming a shell of light. There are no stable orbits this close to a black hole, so photons will inevitably spiral inwards or outwards. As outspiraling light escapes the photon sphere, it joins with severely lensed light from any surrounding whirlpool of hot plasma to form a bright ring around the black hole. This ultimate gravitational lensing has not yet been observed, but real lensing simulations show us what black holes should look like up close. Both the black hole and the wormhole from the movie Interstellar are amazing examples. Next time you look up at the sky, remember, your eye is following strange curved paths. The stars are mostly where you see them, mostly. But look through a telescope at very distant galaxies, and all are brightened, shifted, and warped by the weird lens of a curved spacetime. I guess gravitational lensing is pretty cool. Who am I kidding? It is awesome. In fact, it's one of my main areas of research as an astrophysicist. If you want to learn more about what I'm up to with that, check out the mini documentary I made with the American Museum of Natural History. Link in the description. Okay, we recently started talking about quantum physics by looking at the bizarre phenomenon of quantum tunneling. Let's see what you guys had to say. Flynn Kruchell would like to know whether he really can teleport to the moon. Actually, no. You can't quantum tunnel to the moon because to properly tunnel, you need to spontaneously find yourself at a point in your wave function that has an equal or lower energy state than your starting point. Think about that alpha particle trying to tunnel through the potential energy wall of the strong nuclear force. An exponentially decaying part of its wave function is actually inside that wall. The particle can find itself located anywhere that its wave function is non-zero. That means it can spontaneously be in the region of the wall where the strong nuclear force is pulling it back towards the center. But to escape, it needs to tunnel all the way to the other side, where it finds itself in a lower energy state. Same with trying to tunnel out of a gravitational field. You'd be tunneling to a higher energy state, which is impossible. AyyElMao asks whether my interpretation of the de Broglie wavelength as a range of possible locations is only true for the Copenhagen interpretation of quantum mechanics. Okay, so some of the language I used to describe the collapse of the wave function and possible positions did echo the Copenhagen interpretation, but I don't necessarily endorse it. For those of you who are unfamiliar, the Copenhagen interpretation was one of the early interpretations of some of the weird quantum effects developed in the 1920s. The idea is that a physical system doesn't have the familiar classical properties like position, momentum, spin, etc. until it is observed. Prior to that, it exists only as its wave function, which is a distribution of probabilities of these properties. This description of things as probabilities works, but it's also not deterministic, in that in order for the wave function to become a set of physical properties, there needs to be a completely random sampling of its probability distribution. Alternatives exist. The de Broglie-Bohm pilot wave theory, the many worlds interpretation, and others allow a deterministic interpretation of the so-called collapse of the wave function. But from the standpoint of us, the observer, the effect is the same. The wave function that we calculate defines the probability that we will observe a particular set of physical properties. This is something we'll come back to in a lot of detail, so forgive me for my rather crude answer. Mystyc Cheez and others ask, what is really meant by an observation in quantum mechanics? Well, that's a question that physicists have argued about since the 1920s. Observing a quantum system means doing something to it that collapses its wave function into the classical physical properties like position and momentum. Some interpretations suggest that an observation means any interaction that is thermodynamically irreversible, which is another way of saying that a particle's wave function gets so hopelessly mixed with those of other particles that its observable quantum behavior can't be tracked. Again, more on this later. However, one view that's not really favored is the idea that a conscious observer is needed to collapse a wave function. This is absolutely not the standard interpretation of an observation these days.